So welcome back. In this course, we have talked about MOSFETs for use in digital logic. We've talked a little bit about MOSFETs for use in analog or RF electronics. There are other applications of MOSFETs. One of the most important is in power electronic systems. So that's what I'd like to do in this system, is talk about MOSFETs used for an application that we haven't yet considered. So in power electronic systems, we are basically operating the MOSFET as a switch. The MOSFET is either on or off. When the switch is on, we want the resistance of the switch to be as low as possible. When the switch is off, we want the blocking voltage or the breakdown voltage to be as high as possible so that we can apply a large voltage across the terminals and no current will flow. So two very simple considerations: low on resistance, high breakdown voltage. Now there are a variety of applications for power electronic devices, and MOSFETs included. There are low voltage applications where we're talking about tens or hundreds of volts that are used in various types of power supplies, DC to DC conversion, AC to DC conversion, things like that. There are medium voltage applications where we need somewhat larger voltages as blocking voltages. There are applications in motor controls and more applications in electric vehicles. And then there are high voltage applications where we really need very high voltage semiconductor devices. So this is a much different application space than we have been discussing, and we'd like to just get a first acquaintance or a brief look at this application space. Now, there are a number of different types of power semiconductor devices. We should have a whole course on power semiconductor devices and power electronics. Many of the devices that you'll hear about are mentioned here. In this lecture, I'll try just to illustrate some of the key considerations for power semiconductor devices by only talking about one device. The device we will talk about is a MOSFET. It's known as a vertical diffused MOSFET, and I'll just describe it by this acronym, a DMOSFET, for diffused MOSFET. Okay, so we're going to use the MOSFET as a digital on-off switch. MOSFETs have IV characteristics, output characteristics that look like this. We would like to be operating at some low voltage when the switch is closed and get a high current that flows. So the key considerations will be how much current flows at a particular on voltage, and we will be operating here in the linear region of the IV characteristic. The on resistance will be the on voltage divided by the on current. Now in the off state, we'll crank the voltage up very large. Eventually the device will break down. We'd like that breakdown voltage to be as large as possible. So that breakdown will generally be determined by avalanche breakdown in the semiconductor itself. So our device design goals are very simple. We'd like to maximize the on current when the switch is closed. That means minimize the on resistance. We would like to maximize the breakdown voltage, and we'd like to minimize the area, because the larger the area, the more the cost of the silicon die or whatever semiconductor we're using. So we're going to be talking about what's going to be important to us is something we'll call the specific on resistance, which is the product of the resistance times the area. We'd like the resistance to be low, and we'd like the area to be low, both of them. Okay, so if we think about, first of all, how we're going to do this, we could say, well, we want high currents. The way I get high currents in a MOSFET is I have very wide MOSFETs. So we want a lot of MOSFET width. We want high breakdown voltages. To have high breakdown voltages, we want to spread the voltage out along a long distance so that we lower the electric field, and lowering the electric field then keeps it below the critical breakdown field for avalanche multiplication and breakdown. So we'd like to spread the field out over a long distance. Now, if I were to do that in a lateral MOSFET, I'd have a very long channel length. That would take a lot of area. So to achieve these goals, power MOSFETs use a much different type of geometry than the conventional MOSFETs that we've been discussing, either the planar MOSFET or the FinFET. They use what's called a cellular structure. So you can see here There's a lot of area. The width of the MOSFET is around the area of each of these cells. Many of them are connected in parallel. The current is actually a vertical flow. So they use a cellular structure to pack a lot of width in a given area. And then we use current flow. This particular sketch is not really drawn to scale. The vertical dimension is very large to spread the voltage drop out along a large across a large distance to lower the electric fields and increase the breakdown field. So much different structures that we use. Okay, so area must be minimized. We know that the resistance of any resistor is the length of the resistor divided by the area of the resistor, the cross-sectional area for current flow, times the resistivity of the material that the resistor is made from. We're going to be interested in the product of the resistance times area because we want both of them to be small. So that means we're interested in the product of the resistivity times the length of the resistor. This is what we'll call the specific resistance, and this is what we'll consider for a time. So if I have some technology that gives me a certain specific resistance, the units of specific resistance are ohm centimeter squared, resistance times area. Then if I have some target on resistance I need for the application, the area of the die, or the silicon die or semiconductor die that I need in order to achieve this on resistance is going to be given by this simple expression. Area is important because it translates to cost for the power semiconductor device. We want to keep the area as small as we can. Okay, let's look at the transistor itself. So now we're looking at the cross-section of one of these vertical cells in this power MOSFET. And this is what a basic structure might look like. Much different from the transistor, the MOSFETs, than we've been looking at. Let's look carefully step by step through this structure. So there is a source region. We see two sources here. So this is an NPN transistor, and the N-type source, you can see here, is ion implanted to produce the doping. There's a metal source contact. There's another one over here. There is a silicon gate. Polysilicon is used as a heavily doped silicon layer that is almost metallic. There is a gate insulator using SiO2 here underneath that electrode. There is an implanted, it's called a base, but it's actually the P-type channel in our power MOSFET. So this is a P-type implanted region. So now we have an N-type source, we have a P-type channel. We also have a contact. So on these, we typically short the source to the P-type substrate. This P-type region is like the substrate of an N-channel transistor. And that source is shorted. One of the things that does is it prevents a parasitic bipolar transistor from turning on when we don't want it to turn on. There is a top metal which goes over so that both of these source regions are shorted together and connected in parallel. There is an intermediate dielectric here which just makes sure that top metal layer doesn't short the gate itself. There is a drain contact on the bottom of the transistor. So the current flow from source to drain is going to be vertical. The drain is on the bottom. There's a metallic contact there on the bottom. And some metal on the bottom. So that's the basic structure of this diffused MOSFET, this D-MOSFET. So let's look at what happens in the on state. The channel is right here. And when I turn the gate voltage on, I'll produce a channel. Current can flow from the source across the channel, and then it will have to flow vertically out the drain. So the current flow is in this direction. From the source, there are two sources here, across the P-type channel when I've applied a gate voltage that's greater than the threshold voltage, and then down across this lightly doped N region and out the heavily doped N-type drain. Again, you have to recognize that this sketch is not drawn to scale. The vertical dimension is very large compared to the lateral dimensions. That is so that we can spread the voltage drop across a large region and achieve a high breakdown voltage. Okay, now if I think about the on resistance, I want the on resistance to be as small as possible. There are lots of different components to this on resistance. So let's just look on one side, it's symmetrical on the other. There is a series resistance. Any transistor between the metal contact and the N plus source, there will be some metal semiconductor contact resistance. That's what RS is. There is a channel resistance. This is the channel resistance we get in any MOSFET. There is something called a JFET resistance. Now, a JFET, this narrow N region on the top, this is a PN junction. There will be a depletion region around that PN junction so that the current can only flow in the undepleted part of that. That's the way a junction field effect transistor works. So this part of the resistance is called a JFET resistance. Then there is a resistance due to the drift region as the current flows through this long, lightly doped N-type region that's there for breakdown voltage. And finally, there's another resistance in the heavily doped drain and the metal to the heavily doped drain contact that we call the substrate resistance. So there's many components to that, to the resistance in the on state. And a device designer in general would have to look carefully at all of those and try to minimize each one of those to achieve a low on resistance. But if I go to the limit, for example, when I'm looking for a very high voltage MOSFET, the high voltage is going to result from the fact that I have a very long, lightly doped N region where the vertical current is flowing. That means that that diffused resistance, RDR, that lightly doped diffused, the lightly doped drift region, that resistance is going to dominate. So the resistance of that will be the resistivity of that layer times the length of the current flow, which is the thickness of that drift region, divided by the area through which that current flows. Now, it's really a two-dimensional current flow, so it's not clear exactly what the length of the area is, but we can get the idea. There's some effective length and there's some effective cross-sectional area. The specific resistance then will simply be the resistivity of that lightly doped N layer times the length of that lightly doped N region. The length has to be long in order to have a high breakdown voltage, but the long length then will increase the resistance, so that's the fundamental trade-off that we'll be dealing with. So our specific resistance, the product of resistance times length, will simply be 1 over doping of that lightly doped N layer, Q times the mobility of electrons in that lightly doped N layer, times the thickness of that drift region for the MOSFET. So very simple expression, and this is the component that will dominate the on resistance in a high voltage device. Okay, so we've talked about on resistance, and we have a simple expression for the dominant component in a high voltage MOSFET. Let's talk about breakdown voltage. Now, if I look at breakdown voltage, you can see here that I'm going to be applying a large voltage to the drain. I have an N lightly doped layer P structure. This is like an NIP diode. So, in reality, there are 2- and 3-dimensional current flows, but I can get the gist of things by thinking of the breakdown event as occurring as the breakdown voltage of a P plus N minus lightly doped N plus PIN diode. That's a much simpler one-dimensional problem to analyze, and we can make some headway by doing that. So if I have a simple PN diode, we can assume the depletion approximation to find the electric field. We've done depletion approximation before. It'll mostly, the electric field will mostly occur in the lightly doped region. There'll be a very small extent in the heavily doped region. I'm considering a case here where I've designed the device such that the depletion region is exactly the thickness of that lightly doped N region. That won't always be the case, but it's simplest to analyze, so let's do that. We have derived depletion layer formulas before, so we know how to relate the thickness of that depletion layer in the N region to the voltage that we apply across that N region and to the doping density of that N region. The voltage that we're going to apply is the breakdown voltage. We want to know how high that breakdown voltage is. Well, voltage is the integral of electric field versus distance. So voltage is the area under this curve. So we have a simple relation between the voltage and the peak electric field. The peak electric field is going to be the critical field for avalanche breakdown, a material specific parameter that will be different for every semiconductor. We're going to bias this to a voltage at which the peak field reaches the avalanche breakdown voltage. That'll be our breakdown voltage. Okay, so we can solve for the thickness of the region in terms of the breakdown voltage and the critical field, we can put these two expressions together and we come up with a very interesting expression. The breakdown voltage is proportional to the critical field for avalanche breakdown squared divided by 2Q times the doping density. All right. So simple depletion layer analysis gets us there. I'll just point out that we have considered a situation where we're depleted to the full thickness. We just hit the end of the N- region. In general, the electric field profile could be different. If it's lighter doped, we might deplete all the way through to the heavily doped N region. If it's very lightly doped, we have almost a constant electric field inside. Remember, the EDX is minus Q doping density over epsilon. If the doping density is almost zero, the slope of the electric field is almost zero. So in the case we've been considering, the breakdown voltage is proportional to 1 over the doping density. In the other extreme, when the electric field is constant, the doping is very light, the breakdown voltage is simply proportional to the width of the N region. So in general, we would have to consider all of those situations, but it's just some simple depletion layer analysis of a semiconductor device. All right, that's the breakdown voltage, but we're also interested in the on resistance when that region is not broken down. So when that region is not broken down, that's the N- region through which the vertical current flows. We simply have a resistor there with some resistivity that's determined by the mobility and doping density. The length of the region through which the current flows is the thickness of that drift region, and there's a cross-sectional area A. So the specific on resistance is given by a simple expression. Right. So now we want to get back to this trade-off between on resistance and breakdown voltage. We have an expression for the breakdown voltage from depletion layer formula, considering this simple case where we've depleted right to the end of the drift region. Okay. Well, we can use that to solve for the doping density in terms of the critical field and the breakdown voltage. We also had a relation between the breakdown voltage and the peak electric field at the critical field. We can solve that expression for the thickness of this region in terms of the breakdown voltage and the critical field. Okay, we have an expression for the resistance. Okay, so we're now assuming that this depletion region is the thickness of the drift region. We can solve for the thickness of the drift region and insert it in our resistance formula. We know the doping density in terms of the breakdown field and the breakdown voltage, so we can use that here. And we get a simple and very powerful expression for the on resistance as a function of breakdown voltage. So this is a very important relation, which applies generally to lots of other devices as well, which tells us that there is a trade-off between on resistance and breakdown voltage. We want a long region for a high breakdown voltage, but a long region gives us a high on resistance. And the trade-off is described by this relation. The critical field, it depends somewhat on doping density, but it also depends strongly on the semiconductor. So for example, a lightly doped silicon drift layer of 10 to the 15th per cubic centimeter, N-type, would have a breakdown field that you can read off here, which is about 3 times 10 to the 5th volts per centimeter. That's 300,000 volts per centimeter. Now, silicon carbide has a wider band gap. You would expect it to be more resistant to breakdown. It will take a larger field to break it down and create electron hole pairs. In silicon carbide, the breakdown field is about 7 times greater than it is in silicon. All right, so that's going to lead to a significantly higher breakdown voltage because of the higher critical field. So this is the bottom line. This result shows some trade-offs. So for example, if I desire a specific on resistance, I can plug numbers in this relation and I can tell what breakdown voltage I would achieve. If I have a semiconductor like silicon carbide that has a much higher critical field for breakdown, I can achieve the same on resistance at much, much higher breakdown voltages. And gallium nitride, which has an even higher breakdown field, would give me higher yet breakdown voltages. So there's a lot of interest these days in exploring other semiconductors for these very high voltage applications, wider band gap, higher breakdown semiconductors. So those are of great interest in pushing power semiconductor devices up into this regime of very high voltages, too high in many cases for silicon to accommodate. All right, so this is our basic transistor that we've described. We've used it to illustrate many of the key points in power semiconductor devices. It's only one of the devices that people are exploring, but many of the important concepts come out by analyzing that particular device. For those of you that would like to dive deeper into power semiconductor devices, I can point you to a book. This book is specifically focused on silicon carbide, but many of the device considerations and device design considerations are common to silicon or gallium nitride devices as well. So it's a good reference for those of you that want to dive in deeper to power semiconductor devices. All right, so let's summarize our quick look at MOSFETs for power electronics. So the point I wanted to make is that there are important applications for MOSFETs beyond the digital and RF applications that we've focused on in the first 4 units of this course. The geometries and device design considerations that we use for power electronics are much different than those for analog or digital electronics. And this is really a very important, an application area of growing importance that is still continues to advance very rapidly. So it's an important area that we should know something about. All right, in Unit 5, we're talking about a collection of topics. What's next? Well, there are other kinds of transistors. So far, we've only discussed MOSFETs. In the next lecture, I would like to describe another important type of transistor. It's called a HEMT, High Electron Mobility Transistor. We'll talk about HEMTs in the next lecture.